let us discuss Raman activity of H2O, CO2 and N2O molecules. A molecule is considered Raman active if its polarizability changes during a vibrational mode, meaning the electron cloud distribution within the molecule can be distorted when it vibrates, allowing for the detection of a Raman signal. The primary requirement for a molecule to be Raman active is a change in its polarizability during a vibrational mode. Unlike infrared spectroscopy, where a change in dipole moment is necessary for a vibration to be active, in Raman spectroscopy, a change in polarizability is a key selection rule. In carbon dioxide, the symmetric stretching vibration is Raman active, while the asymmetric stretching is IR active due to molecules' centrosymmetric structure. Although they have no dipole moment and are IR inactive, their symmetric stretching vibrations are Raman active. Molecules with a high symmetry can have certain vibrational modes that are Raman inactive due to the rule of mutual exclusion, in which Raman active modes are often IR inactive and vice versa. Even if a molecule is Raman active, the intensity of the Raman signal can be weak, requiring sensitive detection techniques. If a molecule has little or no symmetry, it is a very straightforward matter to decide whether its vibrational modes will be Raman active or inactive. In fact, it is usually correct to assume that all its modes are Raman active. But when the molecule has considerably symmetry, it is not always easy to make the decision whether or not the polarizability changes during the vibration. Water molecule is a simple asymmetric top molecule. Triatomic nonlinear H2O molecule makes an angle with oxygen at the center. Being nonlinear, this molecule possesses oscillating dipole moments, so H2O molecule is IR active. It will have 3n-6 observed absorption bands. Since it's a nonlinear molecule, we are going to use the formula 3n-6. Here n is the number of atoms. For water molecule, n equals 3 atoms. So we will have 3n-6, which is equal to 3 multiplied by 3 minus 6. So that will give us 3 vibration modes. Hence, the water molecule has 3 vibrational degrees of freedom. All the 3 modes of vibrations in water molecule involve changes in dipole moment and changes in polarizability. Hence, they are IR active as well as Raman active. So we have 3 stretching, and this is symmetrical stretching, and second one is asymmetrical stretching, and third one is bending, symmetrical bending scissoring. The wave number corresponds to symmetrical stretching is 3652 per centimeter. For asymmetrical stretching, 3756 per centimeter, whereas for symmetrical bending, it comes around 1595 per centimeter. And this picture shows Raman and IR spectra of H2O molecule. And the figure has been drawn between transmittance and the wave number. And red curve corresponds to IR spectra, whereas the black one corresponds to black curve, corresponds to Raman spectra. And here are the 3 modes. The highest wave number occurs for asymmetric mode is 3756 per centimeter, and the symmetric mode lies on 3652 per centimeter, whereas for the bending mode it comes around 1595 per centimeter. And all the 3 modes will have both Raman active as well as IR active. for H2O molecule. And during the symmetric stretch, the molecule as a whole increases. See, as a whole increases and decreases in size. Thus, the polarizability ellipsoid of H2O molecule may be expected to decrease in size, while the bonds stretch, and to increase while they compress, but to maintain an approximately constant shape. During the asymmetric stretch, both the size and shape remain approximately constant, but the direction of the major axis changes considerably. See here, changes considerably. Whereas in bending stretch, it is the shape of the ellipsoid which changes the most. Thus, if we imagine vibrations of very large amplitude at one extreme, the molecule approaches the linear configurations with the horizontal axis, while at the other extreme it approximates to a diatomic molecule if the atoms are almost coincidental with the vertical axis. Thus, all the three vibrations involve obvious changes in at least one aspect of the polarizability ellipsoid, and all are Raman active. Rule of mutual exclusion for H2O molecule. If a molecule has no center of symmetry, then it will be both Raman active and IR active. Whereas here, H2O molecule has no center of symmetry, and hence it will be Raman active and IR active. So, table it has been given as Raman and IR activities of H2O molecule. So, mode of vibration is nothing but symmetric stretch, Raman active as well IR active. For bending stretch, N2O, Raman active as well IR active. For asymmetric stretch, N3, Raman active as well as IR active. Now let us concentrate on Raman activity of CO2 molecule. Triatomic linear CO2 molecule has 3 atoms, n equals 3. Therefore, the molecule has 3n degrees of freedom. For linear molecules, there will be 3n minus 5 fundamental vibrations. We'll check whether it is a linear or non-linear. Yeah, it's correct. For linear molecules, there will be 3n minus 5 fundamental vibrations. Therefore, 3n minus 5, that will give us 9 minus 5, which is equal to 4. So, thus CO2 molecule will have 4 fundamental vibrations. So, these are the 4 fundamental vibrations. One is symmetrical stretching. So, symmetrical stretching. There is no change in dipole moment, therefore IR inactive, whereas there is change in polarizability, therefore H2O is Raman active. So, in the symmetrical stretching, IR inactive, Raman active. Whereas in the asymmetrical stretching, there is change in dipole moment, therefore IR active, but there is no change in polarizability, therefore Raman inactive. So when you are talking about in-plane bending, there is a change in dipole moment, therefore IR active, but there is no change in polarizability, therefore Raman inactive. And in the last one, out of plane bending, there is a change in dipole moment, therefore IR active, but there is no change in polarizability, therefore Raman inactive. So in all the 3 cases, we have Raman inactive, whereas IR active. In the first case, in symmetrical stretching, Raman active and IR inactive. So this is complement to each other. And look at the picture now, the Raman and IR spectra of CO2 molecule. The figure has been drawn between transmittance and the wave number, and we have and red curve corresponds to IR spectra, whereas the black curve corresponds to Raman spectra. And as we discussed earlier, Raman spectra, Raman active in symmetrical stretching alone. So this shows only we have symmetrical stretching, which lies at the wave number 1330 per centimeter, 1330 per per centimeter. And asymmetric and bending stretches are absent in Raman spectra. Whereas symmetric stretching is absent in IR spectra. See here IR spectra. So we have asymmetric stretching exists and which lies at the wave number 2349 per centimeter and symmetrical bending mode. So there are two modes, in plane and out of plane stretching, and they are all degenerate. So we have the same value here, which lies at the wave number 667 per centimeter. Raman and IR activities of CO2. Mode of vibration. Symmetric stretching, Raman active, IR inactive. Bending stretching, Raman inactive, IR active. Asymmetric stretching, Raman inactive, IR active. So we can have mutual exclusion principle here, mutual exclusion principle. When Raman is active, IR is inactive. Whereas when Raman is inactive, IR spectra is active. So we can have mutual exclusion principle. Let us explain later. Let us consider the linear triatomic molecule CO2 in which the three fundamental vibration modes exist. The extreme and equilibrium configuration of the molecule and their approximate polarizability ellipsoids are illustrated in the figure. The Raman behavior of the symmetric stretching mode N2O is easily decided during the motion. The molecule changes its size and so there is a corresponding fluctuation in the size of the ellipsoid. The motion is thus Raman active. It might be thought that N2 and N3 vibrations are also Raman active because the molecule changes shape during each vibration and hence presumably so does the ellipsoid. However, both these modes are observed to be Raman inactive. Let us consider this example more carefully. One can interpret this idea in terms of change of polarizability with some displacement coordinate and is denoted by the symbol psi. Thus, for a stretching motion xi is a measure of the extension which is nothing but positive xi or compression negative xi of the bond under consideration. While for a bending mode xi measures the displacement of the bond angle from its equilibrium value positive and negative xi referring to opposite displacement directions. If the equilibrium value of the polarizability is alpha naught, center in figure we are going to look into, see center in figure, then when the bonds stretch which is nothing but xi positive, alpha increases, while when the bonds contract negative xi when alpha decreases. Thus we can sketch the variation of alpha with xi as shown in the figure. So here alpha with xi is drawn here, and one can draw d alpha by d psi. So we can d alpha by d psi, and this value the slope exists here. Here the slope exists, whereas the slope becomes 0 here in the second center figure, and in the right side figure also the slope becomes 0. See here we have d alpha by d psi equal to 0, which is nothing but a slope, and here is d psi by d alpha is equal to 0, whereas in the first figure d psi by d alpha by d psi is not equal to 0. So this figure shows the variation of polarizability alpha with the displacement coordinate xi during the three vibration modes of the CO2 molecule. The details of the curve are not important since we are concerned only with the small displacements. It is plain that near the equilibrium position, so this is the equilibrium position where xi equal to 0. So this is your equilibrium position, xi. The curve has a distinct slope where d alpha by d psi is not equal to 0 at xi equal to 0. Consider an example, N1, the first mode, stretching mode. The stretch of a carbon dioxide is as shown in the figure below. Thus, for small displacements, the motion produces change in polarizability and therefore Raman active. For Raman active, d alpha by d psi is not equal to 0. If we now consider the situation for nu2, the bending motion of figure below, we can count the downward displacement. See, this is the downward displacement of the oxygen atoms as negative psi and an upward displacement as positive. Although it is not clear from the diagrams whether the motion causes an increase or a decrease in polarizability, it is plain that the change is exactly the same for both positive and negative psi. Thus, one can plot alpha against psi as shown in the figure, with as before alpha equal to alpha naught at psi equal to 0. So this is at psi equal to 0, alpha becomes alpha naught. For small displacements, we evidently have d alpha by d psi is equal to 0. So here it is at equal to 0 at psi equals 0. Hence, for small displacements, there is evidently no change in polarizability and the motion is Raman inactive. In the case of the asymmetric stretch nu3, which is shown here, the polarizability decreases equally for positive and negative psi. So the plot of polarizability against the psi has the appearance of the figure. Again, d alpha by d psi is equal to 0 for small displacements and the motion is Raman inactive. See again, d alpha by d psi here is equal to 0. So Raman is Raman inactive. In symmetrical stretching vibration, as the name indicates that the symmetry is retained during the vibration. Here the dipole moment of the molecule does not undergo any change while the polarizability of the molecule changes. This vibration is Raman active and IR inactive. In asymmetrical stretching vibration, as the name indicates that the symmetry is destroyed during the vibration. Here the dipole moment of the molecule undergoes a change while the polarizability of the molecule remains unchanged. This vibration is Raman inactive and IR active. In bending vibration, as the name indicates that there is bending of the molecule due to which symmetry is lost. There is a change in the dipole moment of a molecule, but the polarizability of the molecule does not change. This vibration is Raman inactive and IR active. Thus, according to the rule of mutual exclusion, the molecules which are IR active and Raman active or vice versa must possess center of symmetry. These vibrations show that CO2 possesses center of symmetry and it is linear. Rule of mutual exclusion. Infrared and Raman scattering represent two drastically different physical processes. A particular vibration motion of the molecule may produce Raman scattering as well as absorb infrared radiation. In such a case, the same information is obtained from both the methods. However, certain molecular vibrations interact only with IR radiation, whereas certain others show Raman effect. The IR and the Raman activities of different mode of vibration of a molecule depend on its symmetry properties. An analysis of IR and Raman spectra of a large number of molecules leads to an extremely important general rule known as the rule of mutual exclusion. The mutual exclusion rule states that if a molecule has a center of symmetry, only then those vibrations which are antisymmetric with respect to the center of symmetry can be infrared active, and only those vibrations which are symmetric with respect to the center of symmetry can be Raman active. If a molecule has a center of symmetry, then Raman active vibrations are infrared inactive and vice versa. If there is no center of symmetry, then some vibrations may be both Raman and infrared active. The converse of this rule is also true. Observance of Raman and infrared spectra showing no common lines implies that the molecule has a center of symmetry, but a vibration may be Raman active but too weak to be observed. However, if some vibrations are observed to give coincident Raman and infrared absorptions, it is certain that the molecule has no center of symmetry. No normal modes can be both infrared and Raman active in a molecule that possesses a center of symmetry. IR active modes are Raman inactive and Raman active modes are IR inactive. Thus, the extremely valuable structural information is obtainable by comparison of the Raman and infrared spectra of a substance. If a molecule has a center of symmetry, those vibrations which are symmetric with respect to the center of symmetry cannot produce a change in dipole moment. Hence, they will be ion inactive. However, they will be Raman active since they produce changes in polarizability. The vibrations which are antisymmetric with respect to the center of symmetry are IR active, as it can produce a change in dipole moment. Thus, IR and Raman measurements complement each other, and the complete picture of the vibrational problem can only be obtained by using both the techniques. This is the mutual exclusion principle. For example, CO2 symmetric searching vibrations are inactive in infrared but are active in Raman spectra. Similarly, H2, O2, they are all homonuclear diatomic molecules, are infrared inactive but are Raman active. This principle provides information about the determination of the structure of a molecule. If Raman spectra and infrared IR spectra do not show common lines, then according to the rule of mutual exclusion, the molecule must possess center of symmetry. As mutual exclusion rule talks about the Raman and IR spectra, therefore, this rule is helpful in providing information about the structure of a molecule. The following table gives the details of water molecule which does not possess a center of symmetry, and hence all its vibrations are active in both IR and Raman. So IR and Raman activities of normal vibrations of CO2 and H2O molecules both. So the following table gives the details of CO2 and water molecule. So that's a correction here. So CO2 and water molecule. So mode of vibration, symmetric stretching. For CO2, Raman active, IR inactive. Whereas for H2O molecule, Raman active, IR active. The symmetrical bending for CO2 molecule, Raman inactive, IR active, and for H2O molecule, both Raman and IR active. For asymmetrical stretching, for CO2 molecule, Raman inactive and IR active, whereas for H2O molecule, both Raman and IR active. Now let us have one question. State mutual exclusion principle. Which of the following molecules obey this rule? And justify. C3O2, C2H2, NO2, H2O and HCl. And of course already we have explained about the mutual exclusion principle, which says that if a molecule has a center of symmetry, then Raman active vibrations are infrared inactive and vice versa. If there is no center of symmetry, then some vibrations may be both Raman and infrared active. For example, CO2. We have already seen earlier the mode of vibrations for CO2, structural symmetric stretching, Raman active and infrared inactive. And bending, for bending vibration, Raman inactive, infrared active. For asymmetrical stretching, Raman inactive and infrared active. And for C3O2, the structure is like this. All have double bonds. Since center of symmetry is present, IR active vibrations will be Raman inactive or vice versa. So IR active vibrations, Raman inactive. And for C2H2, since center of symmetry is present, IR active vibrations and it will be Raman inactive. And for NO2, there is no center of symmetry and so vibrations may be both Raman and infrared active. And for N2O, since no that there is no center of symmetry, some vibrations may be both Raman active as well infrared active. And for HCl, there is no center of symmetry, so some vibrations may be both Raman and infrared active. Now, determination of structure of N2O molecule. The structure is N and O. See, you have a single bond with N and O. So, number of atoms will be 3. So, degree of freedom 3n minus 5, as it is a linear molecule. So, we have 3 3s are 9, 9 minus 5 is nothing but 4. So, we have 4 modes. So, one is a symmetrical stretching, another one is asymmetrical stretching, and 2 bending stretchings are there. One is in plane and another one is out of plane, just above the plane. So, we have, and this lies in the PR branch, symmetrical stretching. Asymmetrical stretch also lies in the PR branch, whereas bending and above plane and in plane both lie in PQR branch. Let us consider an example of nitrous oxide. Like carbon dioxide, nitrous oxide has 22 electrons. IR and Raman data of N2O show that out of 3 bands of N2O, 2 bands at 2224 per centimeter, which is nothing, which lies asymmetrical stretching, and this wave number 1285 per centimeter, which is nothing but symmetrical stretching, are active in both Raman and IR spectra, while one band at 589 per centimeter, which is the bending stretching, is active only in IR. From this data, it is concluded that N2O molecule does not possess center of symmetry considering the rule of mutual exclusion. Though N2O molecule is linear but does not possess center of symmetry. That is, it's linear but not symmetrical. Hence, from this rule, one can predict the information of the molecule. From the above discussion, it is concluded that from Raman and IR spectra of a triatomic molecule, whether the molecule is linear or not. Infrared and Raman spectra of nitrous oxide. So, the first in tabulation we have the first one is for the first column is for wave number per centimeter. So 589 per centimeter. For infrared, we have strong and peak QR counter, and there is no Raman line here. And for the next one, 1285 per centimeter, the wave number. For infrared, it is very strong PR counter, and this also has very strong polarized for the Raman spectra. And for the last one, 2224 per centimeter, the wave number, for infrared, this one is very strong PR counter, and Raman spectra also shows strong and depolarized. The application of this rule can provide very useful structural information. For example, the fact that the Raman and IR spectra for N2O have signals at the same wave number suggests that the molecule does not have a center of symmetry. This information can be used to conclude that the structure of the molecule is NNO, single bond, but not NON. In addition, some infrared bands have PR contour indicates that the molecule is linear, and it leads to the conclusion that the structure is NNO. The data implies that the molecule has no center of symmetry, and so the structure is not NON. Such a molecule should have 3n minus 5, which is equal to 4 fundamental modes, but 2 of the modes are degenerate. All the 3 different fundamental frequencies should be both infrared and Raman active, but we note that the perpendicular infrared band does not appear in the Raman. Hence, the bending modes are often weak and even unobservable in the Raman. Thus, according to the rule of mutual exclusion, the molecule has no center of symmetry, that is, it does not have the symmetry structure NON because the two bands are common to IR and Raman spectra. So this is not counter, it is contour. Look at contour. So this is not PQ or contour. So that's a printing mistake here. It is contour and this also contour and this is also contour. It's not counter. P or contour. Hence, N2O has an unsymmetrical structure NNO conformed by its rotational spectrum. Further, the observation of PR contours for the two bands indicates that the molecule is linear, and the failure of mutual exclusion principle immediately suggests that the structure is NNO. In conclusion, in general, if it is a linear symmetrical model, it has to obey the rule of mutual exclusion as center of symmetry. If it is pen-symmetric or linear asymmetric types, all the three distinct modes are active in both Raman and IR. In addition, if the molecule is nonlinear, it cannot give rise to infrared bands with PER contours.